All right, in this video, we're going to talk about the TensorFlow, and we're going to start to introduce the linear regression as example. As we know, linear regression is basically means you're going to have y equals w times x plus b, and the task is to determine what's the best value for w and b to mostly describe the whole set of data. So imagine if we have a bunch of data, so we're going to find what's the straight line that will be the formula for all those data. So when you give an x, I should be able to predict what's the y value. So that's the idea. This example, I'm using one of the reference projects that developed by this author, and this is actually a lower level approach. The reason I use this as example is to show you all the steps of the TensorFlow or deep learning. Otherwise, if you directly jump to that, you probably don't understand fully. And the process of a TensorFlow normally will be you will get and clean and split the data into training and test data. And the second one is you're going to define your model. When you define your model, you have to think about what's your best loss function. There are so many different loss functions. For example, you can use absolute loss arrow as a loss function, or you can use square mean of the as a loss function, or you can use entropy as a loss function. For most of the deep learning, they use entropy as a loss function. But in this simple example, we can use basically square mean. So we'll come to that if you don't understand what this means. And then we're going to define the optimizer. The simple ones or easier ones will be the so-called gradient descent, and the more commonly used in deep learning is going to be ADAM, which is adaptive moment estimator. So again, we're going to cover that a little bit later. And then we're going to define the parameters like weight and bias, and then so the whole task of the model is actually running the optimizer and trying to use initially we're going to find a random value for the parameters, and then the loss, we're going to calculate what's the loss function. Based on loss function, calculate how much error we have for the initial estimator, and then because the idea of the optimization is we're trying to run the loss function to the minimal. So once we get a random value for the parameters, then we plug in the data and then find what's the estimated value with the real data, and then find the error. So based on loss function, then we're going to adjust the optimizer. So we go one way or go the other way. If we find the loss function is calculating a smaller value, so we're saying, okay, we got it in the right direction, keep going. If we get a larger error from the loss function, which is the loss function value, then we say, oh, no, it's a wrong direction. Let's change to a different direction. So eventually, we're going to get the parameters that produces the minimal loss errors, and then that will be end of the optimizer. So that will be the whole model. This will be called by actually model.fit. So model.fit is basically running the optimizer and find the optimized parameters. Once we have the model, and then we're going to do the evaluation. So the evaluation will be actually using the test data to see the performance of those model. And then if the performance is acceptable, then we're going to use the predict to predict the actual value for prediction for forecasting. So the most important part is actually the training. So the optimizer becomes the most important part. If we use it right, if we set it all parameters right, or all of those parameters right, we're gonna get probably the best results. So here's the basic idea. Suppose we're using the gradient descent as a optimizer. So basic idea is we're going to have the loss function. The loss function will be some the actual loss will be calculating every time. So we start at the beginning with the initial random value for those parameters, and then we'll calculate what's the arrows. The arrows will be the loss function. Then we find one. Then in the optimizer, it's gonna actually according to the learning steps, and we're gonna find another parameter values, and then calculate the arrow. If arrow goes smaller and smaller, then we'll say, oh, we're in the right direction. Let's keep doing that, and then eventually we may reach to the minimal arrow. In this scenario, it's very, very straightforward. It's pretty much uniform distributed values, and then you see those are actually a curve. So if you go one direction, eventually you're going to reach here. You probably go a few steps more. You will realize, okay, go that way. The arrow actually grows bigger, so it's better going back. So you bounce back and forth a few times. Eventually you settle down at the very bottom. That will be your minimal arrow. So at that time, all your parameters actually are determined. And sometimes you may are not that lucky. Sometimes your learning, your optimizer may end up running something like this. You actually settled to a local low value, not the global low. So in that case, it really depends on your steps, the learning steps. If your step value is very big, then it may end up to it's never find this the minimal value, because it's keep on bounce and back and forth. It's never settled at a very small value. Well, if your steps are very, very slow, then you may end up back and forth right here and eventually settle as a local minimal arrow. And however, sometimes if you are thinking a falling ball, if the ball has a bigger mass, has a momentum, can go through that hurdle, and then go to this global low arrow, then that will actually find the solution. So that's in that case, you are actually use a different optimizer. It's called the adaptive moment estimator. But that's another different optimizer. So in this case, this particular example, we're using a very, very low level, and we actually define our own optimizer. So we're gonna see that in a second. The most of machine learning problems requires a lot of hyperparameter tuning, and we probably cannot show you all of those, but the basically you will adjust those parameters many times, and eventually you are going to find some good values. So here are some general rules for the ways you do. For example, the training loss should essentially steadily decrease, and steadily first, and then settle, right, and settle and reach to the almost zero. That will be the best. And the next one will be actually if the training loss does not converge, then train for more epochs. So more epochs. And then if the training loss decrease too slow, increase the learning rate. And then if the training loss varies widely, decrease the learning rate. And then lowering the learning rate while increase the number of epochs and or the batch size is often a good optimization. And for real-world database data set consisting of a large number of examples, the entire data set might not fit into memory. In such case, you probably need to reduce the batch size to enable batch to fit into memory. So keep in mind, the ideal combination of hyperparameters is actually data dependent. So you must always experiment and verify. So you're going to try and fail. So that's a general rule. So I just formatted this rules. So hopefully that will be a little easier to read. Okay, and here let's do the example. So first of all, we're going to import some of the packages. So we imported the Tensorflow, imported the NumPy, and in this example, we actually randomly generated some values. So in this example, you're going to see that the parameters here we are setting as the display step and the training step are right there, and then we have the learning rate. Normally, you want to try a relative smaller one, or you can try bigger ones, and then you try smaller ones. You're gonna see the difference. So we start from this one, which is in this case is okay. It's good learning rate, and here's our training data. So this is my x, the first point, x, and this is my y. This is second x, second y. So each of the x, y form a x, y in the 2D plane. And the weight and the bias initially we set as random value, just as this curve shows. We initially give a random value of the parameters, and then you can then we're define our the linear regression formula. So this is actually our how do I get y's value based on x value. So the task is to find the optimized w and b. And the mean square error, so this is actually our loss function. So we are passing the two values. So this is actually true value. This is a predictive value by the parameters and a x value. So we get a predictive value. So the idea here is we find the error. So this is the error. So y predict minus y true, that's my error. And however, the error could be positive, could be negative. If we add the errors together, then we may cancel each other. Therefore, in this case, we just simply square the errors to make sure they are positive, and then we can reduce the mean, find the mean square. And then we actually will use the stochastic gradient descent optimizer. Again, this optimizer is a relative older version. These days, many people are using item, but for this example, we just use the old ones. If you want to know what it is, then you can actually watch the YouTube to find out what it is. So the basic idea is you're going to find starting from random value, and then you go either way. Could go this way or go that way. If you go that way, you're going to find your error is bigger than you go the other way. And if you find your error is reducing, then reducing sharply, that means you are on the right track. You keep on going that direction for the parameters, and then you may going up, and then you realize it's getting bigger. Then you go back and forth and back forth, eventually settle at the lowest value. So that's the whole idea of the optimizer. So in this case, we're using the stochastic gradient descent optimizer. That's what we are showing on the picture and the figure. And here's how do we run the optimizer. So while this gradient tape has the value as a g, so we can keep on running the prediction value and get the loss value. Once this is done, and then we're gonna send the loss value and the parameters as a gradient, and the gradient will be sent to the applied gradient in the optimizer. So we basically what it's gonna say with that direction of the parameter change, is the arrow, is the gradient going up or going down. If go up, that means we're in the wrong direction. We got to go the opposite direction. If it's going down, that means we're good. We keep on going the same direction. So this is actually run optimization. This is the most important one. And then here's, once we define all the functions, then we start running this this loop. So as we have the training step, totally we have 1000, and now it's starting from 1 and it ends at 1001. So the steps is going to run all the 1000. For each of them we run optimization, and then for every 50 steps we show the loss and the prediction, and you're going to see the results. So the loss function at the beginning is relative high, and that's the weight, and you will notice that the loss is sharply going down, sharply reduced. That means we're in the right direction. We keep on going that direction, and you see the weight is actually find it closer to the real value eventually, and our loss is eventually becomes small and small. So that's our eventually the right one. Remember, this is every 50 steps we show. Maybe in some of the steps, let's say 950 is this much, and 951 maybe go up a little bit. So our gradient is actually change the parameter, change directions, and then apply to the opposite directions. That will eventually set down the lowest points. And then at last we actually display the results. So we first plot x and y. So those are the points as the red dots. So that's original data, and then we plot the fitted line, which is our w plus x plus b. So the w and b is determined. We know what it is now, and then we're going to apply that formula. It's like apply this formula to the NumPy, and it's element wise, so we can actually calculate, for example, x, when x is this point, the true value is right here, where I'm going to calculate the predicted values right here. When x is right here, the predicted value is this one, and the real value is this one. When x is this one, this is the predicted value, this is real value. So eventually we're going to find this one, and if you add all the arrows together, this line is going to give you the minimal arrows. So that's the whole point. That's how do we do the TensorFlow. I use a very simple example, which is the linear regression, to introduce the concept. Later, we're at the end of the whole units. We're going to show you a more real way to write the TensorFlow without using the lower level ones.